So in this video, I want to basically kind of talk about energy, okay? And so when we define energy in science, energy is basically the ability to do work or an object's ability to do work. Now, I will go into a lot more detail about this in a later video, but I just want to kind of address some of the various units that energy is subscribed to in chemistry, okay? And so one of the measurements of energy is temperature. So when we talk about temperature, temperature is basically is the average kinetic energy that a particular substance have. All right, and so in the United States, we measure temperature in Fahrenheit. Everywhere else in the world, they measure temperature in Celsius. But when it comes to the SI units or the scientific community, we typically measure temperature in what we call Kelvin. Okay, so interesting enough, there's a really close relationship when it comes to Kelvin and Celsius. So it turns out that the unit of Celsius, all right, the unit of Celsius and the unit of Kelvin, it's the same size. Okay, so in other words, if a substance decreases in temperature by 5 degrees Celsius, okay, it also decreases the temperature by 5 Kelvin. So the biggest difference between the two, between Celsius and Kelvin, really, is just the 0 point. Where is 0? So it just turns out that the coldest possible temperature, which is often referred to as absolute 0, okay, it has been given or assigned a 0 Kelvin value. So that simply means that you can't go any lower than 0 Kelvin. There's no negative Kelvin. Okay, so let's kind of talk about the relationship between Celsius and Kelvin just a little bit more detail. So it just turns out that Kelvin is equal to degrees Celsius plus 273. That's the relationship, okay? Or, other words, that degrees Celsius is equal to Kelvin minus 273, okay? And so if you're given the temperature in Celsius and you're trying to figure out what's the temperature in Kelvin, then all you really have to do is just add 273. So like, for example, we could say that water boils at 100 degrees Celsius, right? So what is that in Kelvin? Well, we know that Kelvin is equal to degrees Celsius plus 273. In this case, Kelvin is equal to, so we have the temperature of water when it boils is 100 degrees Celsius plus 273. So we could say that water boils at 373 Kelvin. So it's pretty simple as that, okay? Now, we also need to know how to convert between degrees Fahrenheit and degrees Celsius, all right? Since these two temperature units have different unit size and 0 points, the conversion between the two is a little bit more complicated. And so let me show you how this works. So to figure out degrees Fahrenheit from degrees Celsius, it's basically degrees Fahrenheit is equal to 9/5 of the degrees Celsius plus 32, okay? While if you're trying to go the other way around, as if you're trying to figure out degrees Celsius, well, it is 5 times the sum of the degrees Fahrenheit, or not the sum, the difference between the degrees Fahrenheit minus 32 divided by 9. Okay, so that's the equations in order to convert from one to another. All right, so let's just kind of practice this. As I said, this is a little bit more complicated, so let's just go through about 2 examples so that way we can see how this works. All right, so like for example, let's say a child, all right, my child, I have kids, okay, and then I noticed that they have a temperature of 102.5 degrees Fahrenheit. Obviously, you could tell this child of mine has a fever. So what is this? How this corresponds to the Celsius scale? All right, so what is this in Celsius? Okay, well, as I stated before, Celsius, to find Celsius is equal to 5, all right? You have the degrees Fahrenheit minus 32, so 5 times the degrees Fahrenheit minus 32 all over 9, okay? And so let's go ahead and just plug these numbers into the equation, right? So here is my Fahrenheit, and I'm gonna substitute it for Fahrenheit here. All right, and so when I rewrite this, I have 5 times 102.5 minus 32 over 9. Okay, so I will plug this into the calculator accordingly, and when I do that, I see that my temperature is 39.17 degrees Celsius. All right, so 102.5 degrees Fahrenheit equates to 39.17 degrees Celsius. Let's look at another example. So let's just say that the melting point, all right, so the melting point of gold, okay, of gold is 1067 degrees Celsius. So let's go ahead and convert this to Fahrenheit, okay? Now, to find Fahrenheit, it is 9/5 of the degrees Celsius plus 32, all right? And so so we go ahead and plug this in, and so we have here our degrees Celsius, all right? And so we're gonna substitute that for degrees Celsius here. And so when we rewrite this, we have degrees Fahrenheit equals 9/5 times 1067 plus 32. All right. And you just plug this in your calculators accordingly. And then what you're going to find is that 1067 degrees Celsius equates to 1952 degrees Fahrenheit. So this is the temperature in which gold melts. Okay. Now the second unit that's typically used to measure energy is what we call joule. All right. Now joule is the SI unit of energy, but you will often find that the unit of energy that's also used throughout the world, or at least in the metric system as well, is calorie. All right, and so this is also a measurement of energy. All right, now you guys probably have heard of calorie before, especially when it comes with food, and that calorie is kind of different. All right, and so there are what we have kilocalorie. All right, well, kilocalorie, or here, it's often called a large calorie or called a food calorie. All right, and so 1 kilocalorie or food calorie is 1,000 of, I guess, a small calorie, if you want to say that. Okay, and if you want to equate this to joules itself, we know that for every 1 calorie is equal to 4.184 joules. So that's the relationship between the SI unit for energy and a calorie in of itself. Okay. Now, why is this important? For specifically in when we're talking about specific heat. Okay. So specific heat capacity is basically is described as a substance of how much energy is applied to it to increase 1 gram of it, all right, by either 1 degree Celsius or 1 Kelvin. Okay. Now the specific heat capacity, it greatly varies from one substance to another. All right. So a substance with a low specific heat capacity will heat up more quickly during a period of time versus a substance that has a higher specific heat capacity. So what do I mean by that? All right, so let's look at this chart here. So this chart consists of different metals, or different types of metals, and their specific heat capacities, okay? And so let's just kind of look at this. All right, so here we find that aluminum has a specific heat capacity of 900 joules per kilogram Kelvin, okay? Copper has a specific heat capacity of 389 joules per kilogram Kelvin. Silver has a specific heat capacity of 235 joules per kilogram Kelvin. And then last, you have brass, which has a specific heat capacity of 375 joules per kilogram Kelvin. So what do these numbers mean? Okay, so remember, specific heat capacity is how much energy needs to be applied to raise a certain mass of it by 1 Kelvin or 1 degree Celsius. All right, and so kind of just following along with these units here. All right, so what this is saying is that for aluminum specifically, you need 900 joules of energy to increase 1 kilogram of it by 1 Kelvin temperature, 1 degree Celsius, okay? For copper, you need 389 joules of energy to increase 1 kilogram of copper by 1 Kelvin, okay, or 1 degree Celsius. Same thing with silver. All right, you need 235 joules of energy to increase 1 kilogram of silver by 1 Kelvin, okay? And then same thing with brass, you need 375 joules of energy to increase 1 kilogram of it by 1 Kelvin, all right? And so when you're looking at this simply means that if you were to apply energy to each of these 4 metals at the same time period, what you will find is that silver will heat up the fastest. Why will it heat up the fastest? Well, it only requires 235 joules of energy to increase 1 kilogram of it by 1 degree Kelvin, okay? And at the same time, aluminum is going to heat up the slowest, all right? Why? Compared to the other 4, it needs 900 joules of energy in order to increase 1 kilogram and to increase 1 degree Celsius if you have 1 kilogram of it, all right? And so the higher the specific heat capacity of a substance, the slower it's going to heat up because it's going to require more energy in order to increase the temperature. All right, why is that the case? Different substances are, because there's different substances, its components, its chemical structure is completely different. And so some substances just need more energy than others. All right, and so in this case, silver doesn't need as much energy as copper, brass, or aluminum will in order for it to increase its temperature. Okay? And so, you guys have even seen this in a real life scenario, right? And so, like, for example, you guys, you will have, your pot, right? You're cooking, and in your pot, you have some water, okay? And then, of course, you are heating it up, right? And oftentimes, and you guys have all observed this, that the temperature of the pot is always much higher than the temperature of the water, all right? And that's because the pot is made of, most of the time, it's some form of metal, right? Water's water, all right? And usually metal has a lower specific heat capacity than water. And so if the metal have a lower specific heat capacity than water, then that means the pot is going to heat up faster than what you have here in the water. So the water is going to heat up slower, all right? It just needs more energy in order for the water to increase the temperature. Okay, now let's kind of look at this from a more of a calculation base. So we could calculate all this using this equation. Q equals M times C times delta T. So let's talk about what each of these mean. All right, so Q is in energy, all right? And so your units of energy could either be in joules or it could be in calories, one or the other. You just kind of have to pay attention. All right. M is your mass. All right. And so sometimes your mass could be in grams, and most times you want it in grams. But you'll find it that sometimes it will say in kilograms or whatever the case is. But if that's the case, you will always want to convert it to grams. C is your specific heat capacity. All right. So specific heat capacity can oftentimes comes in various different units, and the units is typically this. And in general, you have energy over mass times temperature. Okay, that's the unit for a specific heat capacity. So it could look like, so here's an example: joules per grams degrees Celsius. So once again, energy over mass times temperature. You could have it where it could be calorie over kilogram Kelvin, okay, or whatever combination of energy over mass times temperature, okay. So the most important thing when you're looking at these problems or when you're working through them, you have to make sure you watch the units, all right, because if not, you'll get the wrong answer. All right. And then lastly, your delta T. All right. Delta T simply means, T obviously is temperature, right? But delta T simply means it's the final temperature minus the initial temperature. And oftentimes, the units for this is either degrees Celsius or Kelvin. It's one or the other, okay? And so this is the equation that we typically use when it comes to measuring heat with specific heat in mind, okay? So let's go ahead and let's kind of work through a couple of examples, and so that way you guys can see how we use this equation, all right? So for example, let's say you have a bathtub, right? Now a bathtub will probably hold about 95 kilograms of water, okay? So the question I want to ask is, well, how much energy is needed to heat up the water from a cold 15 degrees Celsius to a warm 40 degrees Celsius. All right. And so we're going to, in this case, we're going to both figure out the energy in both calorie and joules. So that way you could see how this is worked out in both of these different units, okay? So now, once again, our equation is Q equals M times C times delta T. All right. So what do we know? So, well, first thing we're going to do, just to lay it out, we're going to look for the calorie first. All right. Now, for calorie purposes, all right, it's in this case you will need to know what is the specific heat of water. All right. And so in calorie, the specific heat of water, all right, C for water is 1.00 cal per grams Celsius. Okay, so that's the specific heat for water in this case. All right, so it's basically saying that we're trying to figure out how much energy, so this is our Q, is needed to heat up the water from a cold 15 degrees Celsius to 40 degrees. So this is our temperature here. So that's for our delta T. All right. I already told you from the beginning that we had 95 kilograms of water. So that's my mass there. And then I told you what was the specific heat for water. So we have everything that we need. For those of you who, word problems, it takes a little bit to kind of get through word problems. I highly suggest that you just highlight all your numbers with the units. That way, it's easier for you to figure out exactly what I've given you and what you're looking for. All right. But once again, for this question, I am looking for energy. Okay. Now, like I mentioned earlier, you gotta make sure you look at your units and pay attention to them before you start just throwing in numbers into the equation and calculating. Because if not, then you're really gonna mess yourself up. All right, so like for example, if you notice, this is kilograms, all right, for my mass. But then at the same time, in my specific heat, I have grams. So I need to change something, all right? For my temperature, I got Celsius, and I have Celsius here for my specific heat. So that works out well. And then lastly, and that means that the energy that I'm going to find is going to be in calories, because obviously the specific heat capacity, I have it in calories here. All right, and so let's go ahead convert this kilograms, and I think it'll be easy to convert kilograms to grams. All right, and so we have 95 kilograms, and we know that for every 1 kilogram there are 1,000 grams. Okay, so 95 kilograms times 1,000 is 95,000 grams. Okay, so that's the mass of water. Now, let's go ahead and plug in all our numbers. All right, so Q, all right, which we're looking for, is equal to the mass. Our mass is 95,000 grams, times C, which is our specific heat, which is 1.00 calories per grams degrees Celsius, times the delta T, or the change of T. Remember, the change of T here, and I'm going to kind of do this off the side, is final temperature minus initial temperature. Okay, so your final temperature is 40, because we're trying to get to 40 degrees, minus my initial temperature is 15. All right, so 40 minus 15 gives you 25 degrees Celsius. All right, and so I'm a person who typically likes using units. That way it kind of keeps me in check, and then I know exactly what unit is my answer supposed to be in. All right, and so you will oftentimes find me writing my units and my calculations. And I highly, highly suggest that you learn to do the same thing as well, because then you can always keep your units in check, and you know exactly how to go from what calculations that you need to work through. Okay, so I see my grams here. Grams here will cancel out. One's the numerator, the other is the denominator. Good. My Celsius here and my Celsius here will cancel out because one's the denominator, the other is the numerator. And so that just leads the calories by itself, which that's perfectly fine, because I am trying to find energy. So I know that works. All right. So now when you put this in your calculator accordingly, you will see that the answer is 2.4 times 10 to the 6 calories. All right, so that's how much energy it's going to take for you to heat up 95 kilograms of water from 15 degrees Celsius to 40 degrees Celsius. Okay, now, so this is in calories. So let's go ahead and just kind of redo this in joules, so that way you guys kind of see how this works. All right, so in joules, this is still Q equals, so we still want this in grams. The only difference is that the specific heat of water in joules is 1.184 joules per gram degrees Celsius. So I'm going to write 4.184, I forgot to write grams here, joules per gram degrees Celsius. And then your temperature difference is still 25 degrees Celsius, all right? And so everything is going to cross out accordingly. All right, so that the only thing that you have left is in joules. So then when you plug this into the calculator accordingly, you'll get 9.9 times 10 to the 6 joules. Make sure you always include units in your answers, okay? So that's the first example. So let's do another one, all right? Completely different problem. Now, so let's go ahead and calculate the specific heat of copper. All right, so we have copper. If it takes 23 calories to heat a 5.0 gram sample, okay, from 25 degrees Celsius to 75 degrees Celsius. All right. And so overall, what we're trying to figure out is what is the specific heat of copper. Okay, that's what we're looking for. So let's use the same equation. So you have Q equals M times C times delta T. Okay, so I'm going to go ahead and highlight and see what I got. So I have 23 calories. That's my energy here. All right. I have 5.0 grams. That's my mass. Okay. I have 25 degrees Celsius to 75 degrees Celsius. That together is going to be my delta T. And then lastly, it says, what is the specific heat? So that's my C here. So what it's showing me now is that I need to solve for C. Okay. Now, typically, I'm a type of person, I like to rearrange my equations first before I plug in the numbers. It's just easier in my mind. I highly suggest that you do this too. But let's just go ahead and rearrange this equation so I could get C by itself. So it's algebra, right? Simple algebra. And so when I rearrange the equation, I get that C is equal to Q over M times delta T. Okay, so this is my equation that I'm going to use in order to figure this question out. All right, and so Q is 23 calories. Okay, my mass is 5.0 grams. Okay, my delta T, so final, which is 75, minus initial, which is 25, so that gives me 50 degrees Celsius. All right. And so everything's going to line up accordingly when it comes to the units, which that's what I expect. All right. And so when you put this in the calculator accordingly, you will get 0.092 calorie per grams degree Celsius. So this is the specific heat of copper in calorie per gram degrees Celsius. Okay. Now let's do one more. I know this video is kind of long, but let's look at one more type of problem. All right, where we're using the same equation, but we're going to be solving for something a little bit different. So we have aluminum. Okay, aluminum has a specific heat. Has a specific heat of 0.215 calorie per gram degree Celsius. So when 25.7 calories of heat is added, okay, to 18.4 grams of aluminum at 20 degrees Celsius, what is the final temperature? So this one's just a little bit different, all right? But I think if you think about it, it's really not that bad. Same equation, all right? But just a little bit different, right? So Q equals M times C times delta T, all right? So let's just see what we got here. So in this case, we have specific heat. Tells me what's the specific heat of aluminum. So that's my C. I have energy because it ends with calories. So that's my Q. All right. It tells me what is my mass. So 18.4 grams. All right. But then if you notice, it tells me that I start this at 20 degrees Celsius. What's the final temperature? So that's delta T. All right, so we're gonna have to substitute delta T to help us define what is the final temperature. So I'm gonna rewrite this equation to where I will be looking for delta T. All right, so I have Q equals M times C times, since I'm looking for not delta T, but I'm looking for final temperature, then I'm going to write is TF minus TI. And ultimately, really what I'm looking for is this right here. What is the final temperature? So like I said, I like to rearrange my equations before I start plugging in numbers because it's just easier. I think ultimately it's just easier, period. All right. So let's rearrange this. All right. So when I rearrange this, I'm going to get rid of the, I'm going to divide out my Q divided by my Q times C. So I'm going to divide this out. All right. So when I divide these out, I could put in the other side. Okay. So I have Q over M times C equals TF minus TI. All right, I want TF to be by itself, so I'm going to add out the TI and then place that on the other side here. Okay, so that's gone. So basically what I have is TI, initial temperature, plus Q over M times C equals my final temperature. So that's my equation that I'm going to use. All right, so let's go ahead and plug in these numbers accordingly. All right, so my final temperature is going to be, so it tells you that your initial temperature, all right, from this problem here is 20 degrees Celsius. So I'm going to write 20 degrees Celsius plus, all right, my Q or my energy is 25.7 joules. So 25.7, not joules, calories, all right? And it's going to divide by the mass, which is 18.4 grams. So I'm going to have 18.4 grams times, all right, times my specific heat, which is 0.215. All right, so 0.215 is going to be calories per grams degrees Celsius. All right, so we got to make sure all the units crosses out accordingly, and then they do, right? Because you have grams in this numerator here, grams in the denominator here, that's gone. Calorie in this numerator here, even though it's kind of the numerator of this fraction here, but really it's technically on the denominator, so that one could cross out. This Celsius is a denominator of a denominator, so that's technically a numerator, right? And so that means it will work, it will pair up very well with this Celsius, so you could just simply add them up. And so when you put this in your calculator accordingly and you add up these numbers, you get that your answer is, the final temperature is 26.5 degrees Celsius. All right, and so that's how you will figure this particular question out.